Good day and welcome back for part 5 of our discussion on the definite integral. In our previous videos, we've defined the definite integral in terms of a limit of a Riemann sum. We've worked through multiple examples using this definition, and we've also explored this geometric interpretation of being a net difference of enclosed areas. So what remains is to discuss a few properties of the definite integral that come from these previous discussions. Mainly we can get these from the geometric interpretation, but in some cases we'll have to just reference back to that definition of a limit of a sum. But in either case, let's work through these one by one and just think intuitively why they should be true. So in the first case, the definite integral from a to a of the function f of x. So from our geometric perspective, if we think we have the graph of a function y equals f of x, and we ask you, and it may seem silly, how much area is enclosed underneath this graph from x equals a to x equals a? Note that's just a line which is one-dimensional and has no area. So the value of this integral is simply 0. From a similar geometric perspective, if we're asked about the definite integral of a constant, this is something that we can also picture quite nicely. So if we just suppose c is a nice positive quantity, between a and b, this is a graph of y equals c, we are asking what is the area of this rectangular region? And note it's a rectangle whose height is c and base length is b minus a. So when we evaluate this integral, what we should get back is c times b minus a. And note it's irrelevant the value that you have for the constant c, any such value will give you back the same result. If you're asked to integrate from a to b of a function, you may wonder, how does that relate to integrating from b to a, i.e. you're switching that around? And it turns out that in this case, it forces you to introduce a negative sign. And that comes from the definition of the Riemann sum and how we define our delta x. Similarly, in terms of properties that we get directly from that definition of the derivative, if you want to evaluate the definite integral of a sum of two functions, intuitively it makes sense you can break this up as the sum of the definite integrals. Also, if you have a definite integral of a constant times a function, you can always pull the constant out front of the definite integral. And our last kind of basic property of the definite integral is as follows. If we are integrating from a to c of a function, and we add on to it the integral from c to b of the same function, note intuitively you might notice we have this c and c as the upper and then lower limit of integration respectively. So thinking about this again from the graphical perspective, if we consider the graph of the function y equals f of x, and just for the ease of convenience with the picture, say we're going from a to b and c is some value in between. If you were calculating this enclosed area underneath the function from a to b, you most certainly could calculate how much area is enclosed from a to c, kind of this first integral, and add on to that how much area is enclosed from c to b, the second integral. That is to say, you could just integrate from a to b. And now that we've introduced these basic properties of the definite integral, we have a great opportunity to practice. So you will find 4 bulleted examples over this page and the next in the note packet. What I would like you to do is to pause the video and give yourself approximately 12-15 minutes, as much or as little time as you need, but go through and give an honest attempt to each one of these. And they should in some way, shape, or form come back to using these basic properties that we've just introduced. So hopefully at this point you've paused the video, you've thought about these examples. Remember, you get out of this course what you put into it. Let's go ahead and just go through these one by one and discuss the ideas. So bullet 1, use the fact that the integral from 0 to 10 of f of x equals 17 and the integral from 0 to 8 of f of x equals 12 to determine the integral from 8 to 10 of f of x. So note, if we use our last property of the definite integral, if I go up a little bit we can see it at the top of the screen, the definite integral from 0 to 10 can be written as the integral from 0 to 8 plus the integral from 8 to 10. We know from left to right the first two definite integrals. From 0 to 10 is 17, from 0 to 8 is 12, and we're left with a simple algebraic equation in terms of the one definite integral we would like to find. So subtract 12 from both sides, and the value of that desired definite integral is simply 5. Moving on to the next example, we're given some general information and we'd like to narrow it down to the integral from 0 to 3 of just the function f of x. And we can certainly do that. We just need to start with this given information and apply our above properties. So just working directly below this, we know that we can break this definite integral up over the sum. And when we break it up over the sum, immediately this integral of interest falls out from it. Not only that, if we integrate from a to b of a constant, we know exactly what the value of that definite integral should be. The constant multiplied by the length of the interval. And if we simply now subtract 6 from both sides, we end up with the value of the definite integral of interest. It's 1. So utilizing these properties very quickly and conveniently answers both of these first two questions. So let's go ahead to the next page. For this third bulleted example, we're given a combination of three integrals, and we would like to write it as a single integral. And let's just look at these limits of integration. Minus 2 to 2, 2 to 5, okay, minus 2 to minus 3, with a negative sign in front. But we could go from minus 3 to minus 2, minus 2 to 2, and 2 to 5. So let's go ahead and just rewrite these, and I'm going to actually take this third integral, and I'm going to write that one first for convenience. And simultaneously, if we flip the order of integration, remember that's going to introduce an extra negative sign out front, which turns this negative into a positive. And then cutting and pasting the first two down. So really doing minimal changes to that third integral, just flipping the order of integration. We can now note that we are integrating from minus 3 to minus 2, from minus 2 up to 2, and from 2 to 5. So if we do a double application of that final property of the definite integral we introduced on the previous page, we're really integrating from minus 3 to 5 of the function f of x. And our final example is really asking us to use the geometric interpretation of the definite integral to evaluate. So the suggestion is break the integral up and interpret geometrically. So let's go ahead and do that. To integrate from 0 to 3 of 1 plus the square root of 9 minus x squared, we can think of this as the integral from 0 to 3 of 1 plus the integral from 0 to 3 of 9 minus x squared. And I'll go ahead and immediately take care of this first integral. It's the integral of a constant. And we know from our properties it can be that constant times the length of the interval, i.e. just the area of a rectangle. So that's no problem to handle. This second part, though, this is what requires the geometric interpretation. We're really integrating the function given by y equals 9 minus x squared. So if we could think about this graphically, maybe we could evaluate this definite integral by interpreting as an area. And I'm going to even throw out here that this is something we won't be able to use formulas to evaluate until we get to Calculus 2. A major portion of Calculus 2 focuses in on techniques of integration, and one of these more advanced techniques of integration that come up in Calculus 2 would be necessary to integrate this function. But even using that more advanced technique, it's going to require a half a page of work, so this geometric interpretation is going to be the ideal approach. So what does the graph of this function look like? Well, one thing we can note is if you square both sides and then add x squared to both sides, that would graphically be the equation of a circle with radius 3 centered at the origin. But note, we started off with just positive y values, so this is really the top half of that circle of radius 3 centered at the origin. So graphically, we have the top half of a circle of radius 3 centered at the origin, and we're asked to evaluate the definite integral from 0 to 3. So when x varies from 0 to 3, that would correspond geometrically to the upper right corner of that circle. So just a quarter of it. And the area of a circle of radius 3 would be pi times 3 squared. And the 1/4 is out front because we have 1/4 of that circle. And that leaves us with 3 plus the quantity 9 pi over 4. And that completes our discussion on the definite integral. What we are going to do in our next video is actually go backwards in terms of material. We want to somehow come up with a connection between this definite integral and the derivative that we previously discussed. And the key calculus property that will do that for us is the fundamental theorem of calculus. But in order for us to state and discuss a fundamental theorem of calculus, we need the language and terminology related to antiderivatives, which will be our next topic. So stay tuned and take care.